Okay, because that's just too confusing. So we're going to talk about water auto-ionizes, right? From time to time, water will bump into each other, and you're going to get a hydrogen, H plus and OH minus, that literally becomes an H3O plus, and that's an OH minus, right? It will break apart. This hydrogen will come over here, and it will make your hydronium ion. The concentration, or however many times it happens in a liter of water, is 1 times 10 to the negative 7 for the hydronium ion. 1 times 10 to the negative 7 times in 1 liter. This is the concentration, that's what the brackets means. In 1 liter of water, that's what we'll have. It will be the exact same amount because you had a water that broke in two, so it will be the exact same amount of the OH. Your H and your OH will be the exact same amount. To get the pH, pH is the negative log, so the negative log of that is 7. The negative log of this is 7, so pH plus pOH is equal to 14. And that's where we were. pH plus pOH is equal to 14.
And that's for everything?
That is for everything. And we're going to use that when we do the formulas. The other thing that we have is this is equal to KW. And KW is going to be a concept that is the hardest concept we're going to have today. K is going to be a ratio of your products over your reactants. And it's literally the concentration of the products, in this case, divided by the concentration of reactants.
So is the box concentration?
The brackets that are square mean concentration, yes. Square brackets mean concentration. Concentration has a different name in chemistry. It's called molarity. But because we really haven't learned molarity, I'm calling it concentration, but it's really called molarity. So that's the products divided by the reactants. If you have more products than reactants, will the number be greater than 1 or less than 1? Right? That makes sense. If we have more reactants than products, will the number be greater or smaller than 1? And that's very important. And that may be too conceptual for some people, but that is crazy important. So here, the products are 1 times 10 to the negative 7, right? And 1 times 10 to the negative 7. So if I put the concentration of my products, and I divide by the concentration of reactants, I will get my K for water. However, can water be concentrated? No, you can't concentrate water because water is water. I can concentrate a solution of salt in water because I can add more salt and have something like the Dead Sea that is very, very concentrated. Or I can concentrate more sugar in my lemonade, right? I can add more or less. So I can change those concentrations, but how can I concentrate water? You can't, right? You can't concentrate a solid either. If I have a metal of gold, can I concentrate gold? No, it's gold is gold. I can concentrate. So we take them out of the equation. They become 1 because they cannot be concentrated, or the concentration is just 1. So in this case, the multiplication of those two is gonna give me the dissociation constant for water. Basically, do you expect it to be greater than 1 or less than 1? Because water, when you have water, do you have mostly reactants or mostly products? Mostly dissociated or mostly not? Mostly not, right? So if you were to do this over that, you'll get a number that will be mostly products, so it'll be a big number, or mostly reactants, so it'll be a small number.
Do 2 multiplied by each other, is that KW?
Yes. And the number is mostly reactants, which means my KW is 1 times 10 to the negative what? Does anybody know how to do this? 1 times 10 to the negative 14.
What's KW?
KW is a constant, it's a dissociation constant. It's gonna tell me if water dissociates a lot or a little. And because it's times 10 to the negative 14, it tells me dissociates extremely little. Negative 14 is a tiny number, right? What would you expect the dissociation constant for a weak acid to be? Would you expect it to be really big? Does it dissociate a lot, or does it not dissociate very much? So the dissociation constant for something like vinegar, which is mostly HACs, just one of them dissociated, right? The dissociation constant would be big or small? It's 1.8 times 10 to the negative 5, meaning it's mostly reactants. It's mostly not dissociated, right? Right? I'm calling it reactants, but yeah, it's
So what's gonna be big or small?
the dissociation constant.
The
The products over reactants type, right? Am I gonna have mostly water, or am I gonna have mostly ions? Mostly water. Am I gonna have mostly vinegar, or am I gonna have mostly ions of acetate ion and hydronium, right? It's mostly vinegar. So those cases are very small. What about hydrochloric acid? That's a strong acid. Is it gonna be mostly H and Cl or mostly HCl? H and Cl, so that's a huge dissociation constant. We don't even use it because it's so big. We just assume it all went and dissociated, right?
So the smaller the exponent that log is,
The smaller this number is, the less it dissociates, the smaller your K will be.
I thought it's always equal to 14.
pH plus pOH is 14, but the concentrations are 1 times 10 to the negative 14.
So the smaller the
pH is the number that we use not to have to use these big numbers. We don't want to keep writing 1 times 10 to the negative 7, right? So we write 7, which is a pH, and a pH plus pOH is 14. But the concentration of the H and the concentration of OH equal to a KW that is 1 times 10 to the negative 14.
can the KW be 1 times 10 to the negative 15? Can
No.
it be over 14?
Not at 25 degrees. If I heat up the water and it becomes hot, do you think that it's going to dissociate more or less? More, right? So we'll have the pH will no longer be 7. The pH and the pOH are going to be higher. So it's going to be a different neutral. So we cannot do that. We cannot keep changing factors. We're going to have to assume every time we're measuring pH, the temperature is 25 degrees C. So this will always be the number, and this will always be your pH and your pOHs, right? We're not going to heat it up, or we're not going to do anything.
I'm confused about the dissociation constants though. So the smaller the exponent, the less it dissociates.
So if you have K, if you have mostly it's products over reactants, right? If your products are 10 and your reactants are 1, does it mostly dissociate? Yes, it's mostly products. Because you have a number that is greater than 1. If on the other hand, you have mostly reactants and very little products, that number is going to be less than 1, right? Because you have mostly reactants and very little products. So that's how K works.
What would 1/10 look like in the 1 times 10 to the negative whatever? Would it
What
be
is
negative 10?
1/10 is 0.1.
And 0.1 times 10 to the negative?
No, it's just 0.1 or 1 times 10 to the negative 1.
Okay, then what's 10 over 1?
It's just 10. Or 1 times 10 to the 1.
So the smaller the exponent, the more it dissociates. Or less.
The more negative, so 1 times 10 to the negative 1 is much bigger than 1 times 10 to the negative 14. Right? That's a bigger number than this one. Is that what you were saying?
Just like if you're filling in the blank, the smaller the exponent, the more or the less it dissociates.
If you have 0, 1 times 10 to the 1, 1 times 10 to the negative 1, no, not 0. 1 times 10 to the 1 and 1 times 10 to the negative 1, and then 1 times 10 to the 20 and 1 times 10 to the negative 20. Tell me which one dissociated the most. That dissociated like crazy, and this didn't dissociate at all.
The smaller the exponent, the less it dissociates.
Yes.
And does that mean if it dissociates more or less, does that have to do with how basic or acidic it is?
In water, it's just 1 times 10 to the negative 14. What's going to happen later is going to tell us how weak of an acid it is. So the acid that has a smaller K is going to be much weaker than one that has a bigger K. That's it. Okay, no more of this. Do you have these formulas? These formulas?
Yes.
Okay, so now we should be able to work on those problems that we have on your worksheet.
Is the worksheet online? Like, can I put it at home?
It is online. I can print it right after,
I'm leaving.
but you're leaving. So, so you can print it at home as well.
Okay.
No?
You're good.
So let's do